Picture this. You're standing on the beach, and you're looking up at this massive tidal wave. But it's not water. It's information.
Oh, yeah. A literal flood.
Right. It's the whole artificial intelligence boom of 2026. And you're 23 years old, and you just know that you are in the absolute perfect position to grab a surfboard and ride this thing.
You've got the time, you've got the energy.
Exactly.
Yeah.
But then you look online, and the sheer volume of like tutorials and roadmaps and completely conflicting advice, it just comes crashing down on you. It's totally paralyzing.
It is the absolute definition of information overload. I mean, the landscape is moving so incredibly fast. You want to learn, but finding the actual starting line feels, well, impossible when everyone is pointing in a completely different direction.
So that is our mission today. We're taking that overwhelming wave of noise, and we're just distilling it down for this deep dive. We've pulled together a really massive stack of sources today. We're looking at university-level machine learning guides from UC Berkeley. We've got highly practical engineering roadmaps tailored for 2026.
Justin Skycack's foundational guides, too.
Yes, his math and machine learning guides, plus Jason Brownlee's textbook on coding algorithms from scratch, and some incredibly grounded field guides on avoiding those rookie mistakes that will literally get you fired.
And by synthesizing all of those different perspectives, we are going to build a concrete step-by-step roadmap. The goal here is to take you from like a high school math level all the way to building cutting-edge deployable AI systems.
Okay, let's unpack this. Because before you even think about opening a code editor or, watching a Python tutorial,
Right.
our sources point out this fundamental choice you have to make.
The fork in the road.
Right, there's a fork in the road right at the very beginning of your career journey. You have to decide what game you're actually playing.
Yeah, both the Syracuse University curriculum and the AI weekly roadmaps emphasize this heavily. They basically separate the AI landscape into two totally distinct learning paths. You have the power user and you have the builder.
And from what I'm reading, these are completely different beasts. I mean, the power user path doesn't seem to require any coding background at all.
Right, zero code. None.
That's wild. The roadmap suggests you can become highly proficient in a matter of days, and it's entirely focused on mastering prompt design.
Yeah, and Syracuse actually outlines a specific framework for this that I found really interesting.
Oh, the RCTCF thing?
Exactly. It's role plus context plus task plus constraints plus format.
Okay, break that down for me.
So that framework essentially forces you to stop treating the AI like a Google search bar. You have to start treating it like a specialized employee. If you just ask for a marketing email, you get generic garbage.
Right, it sounds like a robot wrote it.
Exactly. But if you assign it the role of a senior copywriter, give it the context of your specific product launch, assign the task of writing an email, add the constraint of a strict 200-word limit, and then ask for the format in HTML.
Suddenly the output is professional grade.
Exactly. The precision just completely changes the result.
It really does. But there was another technique in the power user guides that caught my eye. The XML sandwich.
Ah, yes. The XML sandwich.
I mean, I get that it involves using tags to format text, but why does the AI need us to literally sandwich our data in code tags? Like, is it really that easily confused?
Well, think about how a human reads a document. We have a visual cortex, right? We see a bold header or a box drawn around a paragraph, and we instantly know, okay, this is the instruction, and that text below it is the raw data I'm supposed to look at.
Right, we just see the layout.
Yeah, but an AI model doesn't have eyes. It reads everything as a single, flat, continuous stream of text tokens.
So if I just paste like a messy transcript into a prompt and say, summarize this, the AI might accidentally read a line of the transcript as a command?
It happens all the time. The AI just gets lost in the context. So the XML sandwich solves this by using simple structural tags, putting the word document inside angle brackets at the start of your data and a closing tag at the end.
Oh, I see. So you are artificially creating that visual boundary.
Precisely. You are strictly separating your instructions from the raw information. It drastically reduces errors and keeps the model focused.
It's such a simple trick, but it totally makes sense when you remember the AI is just crunching text sequentially. But okay, let's look at the other side of that fork in the road, the builder path.
Hey, the heavy lifting.
Yeah, this is for the listener who wants the actual title of AI engineer or machine learning engineer. And the AI weekly roadmap, I mean, It does not sugarcoat this at all. We are talking about learning Python, tackling serious math, and committing to roughly 400 to 500 hours of focused study over 6 to 12 months.
It is a massive commitment. It's the fundamental difference between knowing how to operate a piece of heavy machinery and knowing how to design and manufacture one.
Here's where it gets really interesting to me, though.
Yeah.
If I'm 23 and I'm trying to build my career from scratch, do I really have to choose just one path?
You mean, do you have to pick between being a power user or a builder?
Yeah. It feels like a false dichotomy. To use an analogy, the power user is the person driving the Ferrari, but the builder is the mechanic who actually understands how the engine works. Why couldn't I drive the car to work every day while taking night classes to become the mechanic?
I love that analogy. And the reality is, not only can you do both, but operating the vehicle first is arguably a mandatory prerequisite for the builder path.
Wait, really? Mandatory?
Yeah, because by mastering advanced prompting and pushing the absolute limits of existing models, you're building essential AI literacy. You develop a deep, intuitive understanding of what these large language models are actually capable of, where they fail, how they handle edge cases.
Okay, that makes sense. You need to feel how the car handles on the road before you start taking the engine apart in the garage.
Exactly.
So let's say you've done that. You're a power user. You know the limits. Now you are opening the hood to become a builder. This leads us into what I think is easily the most intimidating part of the journey. The unsexy foundation.
Ah, yes, the underlying math and classical machine learning.
Yeah, because the temptation is to just skip straight to the sexy stuff.
Yeah.
You want to build the next viral ChatGPT clone or some cool multi-agent system.
Of course. That's the fun part.
But Justin Skycak's roadmap drops a hard truth. You cannot skip the math. We're talking high school algebra, calculus, probability, and statistics. He claims that without this foundation, reading a cutting-edge AI research paper is like trying to read ancient hieroglyphics.
And honestly, he isn't exaggerating. And the goal here isn't just to memorize formulas to pass a test, right? It's about understanding the mechanical reality of how a machine actually learns.
He's used calculus as an example because I'll admit my eyes totally glazed over a bit when I saw that on the curriculum.
A lot of people have that reaction.
Yeah. But there was this one video transcript in our sources that used an analogy I'm really trying to wrap my head around. They talked about training an AI using something called gradient descent. And they pictured this massive, multi-dimensional parabolic bowl. I'm trying to visualize this. So the bottom of the bowl is zero error, right? Total perfection.
That's a great way to visualize it. When you first initialize an AI model, it knows absolutely nothing. So mathematically, it starts somewhere way up high on the rim of that bowl, just making terrible predictions and generating massive amounts of error.
But how does it actually find its way down? It's not like the AI has a map of the bowl.
It doesn't have a map, and it is entirely blind. Imagine you are blindfolded on a rugged mountain, and your goal is to reach the valley floor. What do?
I guess I'd feel the ground with my foot and step downhill.
Exactly. You feel the ground immediately around your feet, find the direction that slopes downward the steepest, and you take a single step. That is exactly what calculus does for the AI.
Oh, wow.
Yeah, it calculates the derivative, which is just the slope of the error surface at that exact moment. The model adjusts its internal weights, taking step after step down the steepest slope, literally descending the gradient until it hits the bottom where the error is minimized.
Wow. Okay, so if you don't know calculus, that entire learning process is just magic. It's a black box. You have no idea how the machine is actually improving.
Exactly. And that black box mentality becomes incredibly dangerous when we start talking about the curse of dimensionality.
Oh, right. The UC Berkeley guide highlighted this as a major stumbling block. This is that concept where human intuition just utterly fails us.
It really does.
I found this part mind-blowing, but honestly also a bit confusing. How exactly does human intuition break down when we deal with AI data?
Well, we evolved to navigate a three-dimensional world, right? Think about a 3D sphere, like a solid orange. In 3 dimensions, the meat of the orange is distributed pretty evenly throughout the whole shape.
Right, it's solid all the way through.
But AI models don't operate in 3 dimensions. They analyze data across hundreds or thousands of dimensions simultaneously.
And the geometry actually changes.
The math gets incredibly weird. In high-dimensional spaces, the volume of a sphere doesn't stay evenly distributed. Almost all of the volume gets pushed outward to the very edge, to the crust.
Wait, so the inside of a high-dimensional orange is basically hollow?
For all practical purposes, yeah.
Yeah, it is crazy.
And the consequence of that is massive. Our human brains assume that if we gather a bunch of data points, they will cluster together and be relatively close to one another. But in the high-dimensional spaces where AI lives, data points are incredibly far apart and isolated on that outer crust.
Wow.
If you don't understand the underlying mathematics of that space, you will try to use traditional data analysis techniques that will fail catastrophically, because your assumptions about distance and similarity are fundamentally false.
Which perfectly explains why Jason Brownlee's textbook insists that you have to implement classical machine learning algorithms entirely from scratch.
Yes, absolutely no shortcuts.
He literally wants you coding a simple linear regression, which is, what, a 200-year-old math concept?
Yeah.
Entirely in Python. But let me play devil's advocate for the 23-year-old listener who just wants a job right now.
Fair enough.
Why would I spend hours agonizing over the code for a basic linear regression when massive, highly optimized libraries like PyTorch already exist? I mean, I can literally import a state-of-the-art model in one line of code.
It comes down to developing a sixth sense for the architecture. Justin Skycack uses a fantastic analogy here involving a jazz musician.
Okay.
Think of a master jazz pianist who has spent years locked in a practice room, just endlessly repeating boring scales, arpeggios, and chord progressions.
The unsexy foundation.
Precisely. Because they have drilled that deep structural foundation into their muscle memory, they can walk into a club, sit down at a jam session, and flawlessly improvise over a song they have never heard before.
Right, they aren't thinking about individual notes anymore.
You just feel the underlying structure of the music.
So the developer who codes classical ML from scratch is just practicing their scales.
They are developing an intuition for the micro decisions happening under the hood. So later in their career, when they finally have to read a dense, cutting-edge AI paper, the equations aren't hieroglyphics. The architectural patterns just jump out at them intuitively.
Okay, so let's say I'm that developer. I've put in the hours, I've practiced my scales, I survived calculus, and I have my Python foundation. What next? Because the industry isn't hiring people just to write linear regressions. I need the actual 2026 skill set. What are employers specifically looking for right now?
Well, according to Sarah Marino's generative AI skill set roadmap for 2026, the landscape has shifted drastically away from what most people expect.
How so?
Everyone assumes you need to be an expert in training massive foundational models, but her breakdown is shocking. LLM foundations only make up 30% of the required skill set. Agentic AI and workflow automation make up 40%.
40%. That is a massive chunk of the pie. We should probably define that clearly. Actually, the word agent gets thrown around a lot. What separates a standard AI chatbot from agentic AI?
The key differentiator is autonomy and the ability to use tools. A standard chatbot is passive. You ask it a question, it generates a text response, and it stops. It is entirely dependent on you to drive the interaction.
Yep.
Agentic AI refers to systems where you provide a high-level goal, and the agent autonomously reasons through the problem, creates a step-by-step plan, and then actively utilizes external tools to execute that plan.
Give me a real-world example of what that looks like.
Okay, so instead of asking a chatbot to write a generic email template, you give an agentic system a goal, like close a meeting with the CEO of this specific tech startup.
Okay.
The agent will autonomously use a web search tool to find the CEO's recent podcast interviews, use a data scraping tool to pull their company's latest quarterly earnings, write a highly personalized email based on that data, open your email client via an API, draft the message, and just wait for your approval to hit send.
That is wild. But building a system that can do all of that sounds less like machine learning and more like, I don't know, traditional back-end software development.
And that is the secret most beginners miss.
Mm-hmm.
The AI Engineer Roadmap by Balapriya C. emphasizes this heavily. To be a successful AI engineer in 2026, you mostly just need to be a rock-solid traditional software engineer. You're basically bolting AI components onto traditional architecture.
That makes total sense. She mentions needing to master back-end frameworks like FastAPI, understanding Docker for containerization, and writing rigorous tests with PyTest. Because having a genius AI agent doesn't really matter if the server it lives on crashes every 5 minutes.
Exactly. The industry term for this is orchestration. Modern AI engineering isn't really about tweaking the neural network itself. It's entirely about how you orchestrate the environment around the model. For instance, how are you handling memory?
Right.
If a user talks to your agent today, does the agent remember the context of a conversation they had 3 weeks ago?
And I imagine error handling is huge here, too. Like, if the agent is trying to autonomously search the web, what happens when the Google API times out?
Precisely. A fragile demo will just crash and spit out an error code. Real software requires robust logic, like implementing retries with exponential backoff.
Exponential backup.
Yeah, where the system waits 1 second, then 2, then 4 before trying the API again. That scaffolding is the real 2026 skill set.
I see. And reading through these roadmaps, a huge part of that orchestration involves something called R retrieval augmented generation and vector databases.
Yes, absolutely crucial.
Now, I understand the problem RA is trying to solve. LLMs hallucinate because they are basically taking a closed book test. They rely on their vast, fuzzy, pre-trained memory to answer questions, and sometimes they just guess. So RA is meant to turn it into an open book test by forcing the AI to look at your specific documents.
That's a perfect analogy. You are giving the AI the exact textbook and saying, only answer using the information on these specific pages.
But the mechanics of how it finds the right page is where I get lost. The sources say you have to use a vector database, like Chroma. And this word embeddings keeps popping up. How do you take a PDF document and put it into a database so the AI can read it?
Well, you have to translate the human language into the mathematical language the AI understands. You take your PDF and you chop it up into small chunks, maybe a few paragraphs each.
Okay.
Then you run those chunks through an embedding model. This model analyzes the semantic meaning of the text and converts it into a long list of numbers, which acts as a set of coordinates in a high-dimensional space. That list of numbers is the embedding.
Wait, so you are literally turning the meaning of a paragraph into a coordinate on a map?
Exactly. And you store all those coordinates in the vector database. Then, when a user asks a question, you turn their question into a coordinate as well.
Oh, I see where this is going.
Yeah, the vector database simply measures the mathematical distance between the question's coordinate and the document chunk's coordinates. It grabs the chunks that are physically closest in that mathematical space, hands those specific paragraphs to the AI, and says, here is the relevant context. Draft your answer from this.
That is brilliant. It completely bypasses the fuzzy memory problem by grounding the AI in mathematically verifiable relevance.
It really does.
So, okay, you know the math. You understand RAG vector databases and how to orchestrate agents. Are you ready to start applying for those 2026 engineering roles?
On paper, yes. But in reality, this is the exact moment where the vast majority of learners get trapped in what Irene Holden calls tutorial hell.
Tutorial hell. I love that term because it is so painfully relatable. You can follow step-by-step guides all day, but the second you try to build something on your own, your brain just goes blank.
Holden's guide is incredibly blunt about why this happens. She compares coding tutorials to watching a high-end cooking show. The kitchen is immaculate, all the ingredients are pre-measured in perfect little glass bowls, and the oven is already preheated.
But real-world coding is nothing like that. It's a chaotic, messy kitchen. The pan is spitting hot oil, the smoke alarm is going off, your data is completely unformatted, the API keys keep getting rejected, and the model is spitting out absolute gibberish.
And when that chaos hits, beginners usually panic. They suffer from imposter syndrome. They think they lack the innate intelligence to be an engineer, when in reality, they just haven't practiced dealing with the mess.
You're right.
The only way out of tutorial hell is to build a real portfolio project entirely on your own.
But Holden notes that when beginners finally try to build something, they almost always build the wrong thing. Scope creep destroys them. They try to build a massive, all-encompassing general productivity assistant.
Specificity is the absolute antidote to scope creep. Her golden rule is vital here. Pick one real user and solve one specific problem. Don't build a vague tool for everyone. Build a highly specific tool that helps your college roommate search their messy SQL lecture PDFs.
And she also warns against getting bogged down in massive data sets, right? Beginners think they need to scrape gigabytes of data from the internet to prove they know machine learning.
That is a massive time sink. She advises using perfect starter data just to prove the architecture works end to end. If you are building a RAG application, literally just use 5 to 10 PDFs.
Keep it simple.
Exactly. If you are building an object detection model using YOLO, use a clean set of 50 to 200 images. Your goal isn't to train a world-class model. Your goal is to build a functional system. Wrap it in a simple user interface using a tool like Streamlit, and deploy it to a live URL so recruiters can actually click a link and use it.
Which brings up the 10-20-70 rule she mentions for real-world AI projects. When I read this, it completely reframed how I view the job of an AI engineer.
It is a sobering breakdown. In a real-world project, only 10% of the actual work is the machine learning algorithm itself.
10%. After all that math we talked about.
Yeah. 20% of the work is sourcing, cleaning, and formatting the data so the model can actually digest it. And a massive 70% of the work is the traditional software engineering we talked about earlier. The system wiring, the API integrations, the error handling, the user interface, and the deployment.
It sounds like beginners try to open a 5-star Michelin-rated restaurant on day one when they really just need to prove they can cook a decent dinner for 2 friends without burning the house down.
That's it exactly. Ship something small, ugly, and reliable. That is how you get hired.
Okay, so you are finally out of tutorial hell. You are building real tools that real people are using. But as you transition into the professional world, the stakes get significantly higher. Which brings us to Marcin Piekarski's Field Guide to AI.
Oh, the 10 common AI mistakes.
Yeah, and a few of these aren't just minor bugs. They're absolute career killers.
The very first mistake he highlights sounds almost insulting, but it is the trap we all fall into. Expecting the AI to have human common sense.
We absolutely all do it. The interfaces are designed to be conversational, so we instinctively talk to it like it's a person. We just assume it understands the physical world.
But Piekarski forcefully reminds us that it does not know anything. It has no lived experience. It is purely a statistical engine predicting the next most likely word based on patterns in its training data.
Which feeds right into mistake number 3, trusting outputs without verifying them. Because it is a pattern prediction machine, it can generate text that sounds incredibly confident, highly authoritative, and entirely plausible, but is completely fabricated.
The classic hallucination. The example he gives in the guide should be a warning to every junior employee out there.
It was terrifying. A user asked the AI for statistics from a 2021 Stanford study on remote work productivity, and the AI confidently spits out a multi-paragraph summary, complete with specific percentages, detailed findings, and a compelling conclusion. The problem: that study does not exist. Nope. Completely made up.
The AI completely invented it because the statistical patterns of the prompt demanded a realistic-sounding academic response. If you copy-paste that hallucination into a market research report for your boss, well, you're packing up your desk.
You must develop the habit of ruthlessly verifying specifics. Dates, names, academic citations, legal precedents. These are hallucination magnets. But as bad as that is, mistake number 5 is perhaps the most dangerous from a corporate liability standpoint.
Ignoring privacy and data security.
Yes.
Oh man, the data leak nightmare scenario. The guide paints this picture. A junior developer is working late. They're stuck on a complex bug, so they copy-paste a huge chunk of their company's proprietary code into ChatGPT to ask for debugging help.
Which is a very common practice, but incredibly risky.
Because they accidentally leave their live AWS API keys embedded in that code snippet. By hitting send, they just log the keys to their company's entire back-end cloud infrastructure directly into OpenAI's servers. It is a massive, highly actionable security breach. As an AI engineer, you must constantly train yourself to redact sensitive information, personally identifiable data, and security keys before they ever touch a prompt.
So I have to ask, looking at all of this, if I'm listening to this deep dive, I'm thinking, okay, the AI regularly hallucinates fake research. It possesses absolutely zero actual common sense, and it represents a massive data leak risk for any company using it. Aren't we building our entire 2026 careers on a foundation of quicksand?
It is a very valid fear, and it's why the hype cycle can be so dangerous. But if we connect this to the bigger picture, you have to remember what AI fundamentally is and what it isn't. AI is a tool designed to inform, not to decide.
Inform, not decide. Let's test that. What does that mean in practice?
It means playing to the tool's strengths. It is unparalleled at brainstorming ideas, drafting boilerplate codes, summarizing massive troves of documents, and surfacing options at lightning speed. But it is fundamentally terrible at high-stakes, nuanced decisions that require ethical weighing, cultural context, and human values.
So you don't trust the AI to autonomously fire an employee, or diagnose a terminal disease, or execute a massive financial trade?
Never. You use the AI to gather and synthesize the data so the human operator can make a better, faster, more informed decision. The true value of an AI engineer in 2026 isn't just knowing how to wire the models together, it's knowing exactly where the model's competence ends and architecting the system so that human judgment is firmly inserted back into the loop at the critical moments.
So to the 23-year-old listening right now, staring up at that massive wave of information, you have the 400 to 500 hours it takes to conquer this? The roadmap is actually remarkably clear when you strip away the noise. Choose your path. Master the prompts as a power user, and if you want to build, lay down the unsexy mathematical and Python foundations. Put in the time in the practice room. Then, master the skill set that actually matters in 2026. orchestration, RG, and agentic workflows. Escape tutorial hell by building one highly specific, messy, deployed project for a single user. And above all, guard your systems against hallucinations and data leaks by keeping the human in the loop.
It is a profound, challenging journey, and as you embark on it, I want to leave you with a final concept from Justin Skycak's Guide to Mull Over. He discusses a phenomenon in cognitive science called the expertise reversal effect.
The expertise reversal effect. How does that work?
When you are a total beginner, highly structured, step-by-step tutorials are incredibly beneficial. They reduce your cognitive load, prevent you from getting overwhelmed, and help you learn the basic mechanics safely. But, and this is the crucial part, as you build your foundational skills and begin to transition into an expert, those exact same step-by-step guides will actually hinder your learning.
Because they stop you from struggling. They become a crutch that prevents you from developing your own intuition.
Exactly. The structure that once saved you becomes a cage. So the question you have to constantly ask yourself on this journey is, when will you recognize that you have outgrown the tutorials? When will you be ready to throw away the roadmaps, step completely into the unstructured, messy unknown, and start breaking things entirely on your own?
Because the moment you are willing to step into the unknown, that is the moment you stop looking up at the wave and you finally start riding it.